Hi, in this series of tutorials, I will be talking about PyTorch and how we can do neural networks and physics-informed neural networks and other types of modeling in PyTorch. So I will start in the first example as a purely data-driven and deep neural network model that can map an image type scientific data to another image type scientific data. And I'll walk you through this code, how we can train and test this model. So the example that I selected is a super resolution example. So let's say we have a CFD simulation for a blood flow in this simple 2D example, a 2D stenosis. So here you're looking at the velocity that the flow goes from left to right. And this is a low resolution example. So we have a low fidelity data set. It's, it's, as you can see, it has a very, very coarse mesh. And also in the solver setting that I use in running this simulation in FEniCS, I use lower fidelity solver settings, and also I use more dissipative viscosity. So it's a really low fidelity approximation to the solution. And my goal is to learn a mapping that maps this low fidelity data to this corresponding high fidelity data, which comes from a high fidelity solver setting and also a very fine mesh. So I can zoom into the mesh and you can see the very fine mesh in this high fidelity data. And what I have is that I have 400 sets of simulations so I can play. So these are for different Reynolds numbers. So I have 400 different sets of data, pairs of data that I want to learn a map. Okay, so here's the code. So I'm using PyTorch here, and also I'm also using VTK libraries for reading this VTK data that I need for my training, and I'll provide a link to this data set that you can also work with. So here at the top, I'm first defining different classes of neural networks. So I've defined a few different ones here that you can take a look at. So just to provide some examples, for example, we could either do this by using a convolutional neural network. So here's this class, myCNN is an example of a convolutional neural network. So you have different convolution layers. You have ReLU nonlinearity added after each layer. And then, these convolution layers essentially extract features in your image data, and then you follow that by some fully connected layers that map those features to the output that you would like. So essentially, they provide the mapping. So, so here you define these different layers. You have these different activation functions, and then you go to these, fully connected layers. And in the forward part of this class, we assemble these next to each other. So we go from an input X to different intermediate outputs out, and we keep doing this until we go to the last output and we return that, which is, in this case, this last one here. Now, when you go, so the main one thing you need to pay attention is that when you go from these convolution layers to the fully connected layers that follow, you need to set this first layer number here such that it's it's basically set based on how many channels you have and other parameters there. That there's a formula you can calculate that. But if you set this wrong, PyTorch will give you an error. From that error, you'll know what the correct value is. But the last layer should map your input to the desired output. So in this case, I have a 28 by 28 image, which essentially I'm considering it as a flat column. Okay, so that's my output. Okay, so then I have also different examples. Here's an example of an autoencoder type model. I have a fully connected autoencoder here. So here's perhaps a fully connected neural network is a simpler example that you could design. So here it's just a fully connected neural network. It starts by 28 by 28 data set. It maps it from to 256 layer. It applies a ReLU activation function, then maps 256 to 128. It keeps going until it reaches 8. So this is an autoencoder style. We're starting large and we're going to a latent space. And this architecture allows us to learn meaningful representations of the data because you're forcing the network to pass through this bottleneck essentially here, which is I select a size 8. Okay. So the smaller you set that, essentially a more reduced order model you can think about that neural network discovery. And then in the decoder part, I start with the 8 and then go back up And I can select how many layers I want to go back up. It doesn't necessarily have to be similar to the encoder. So I'm going from 8 to 32, 32 to 64, and then finally 64 to the desired output size, which is my image resolution that I want to learn. And I can, of course, do this in different ways, okay? So then I have a bunch of other functions here, which are for processing image type data, which I don't use in this tutorial. And then I have defined my directories. This is the directory for input VTK files, the low resolution files, the directory for outputs. So you need to, of course, update these directories when you want to test this. So I'm writing my output to a PT file called this. And so this is the output of the neural network. So essentially, this PT file saves all the parameters of your neural network. And in a later tutorial, I will show you how you can convert that PT file to a VTK that you can, visualize in parallel. Okay, so here in this example, I have 400 files. I'm selecting 80 of them to be used for validation. So the number of training is calculated as such. I am using a structured mesh here because so essentially what I'm doing is that I'm defining this domain, this small 2D domain, which is a subset of my domain. So basically, it's somewhere here, a square domain in my region, in my data. So I'm defining it here, and what I'm going to do next is that I'm going to interpolate my data to that, structured mesh, okay, for both low res and high res, and learning mapping from there, okay. And here I'm using some normalization factors to ensure my data are normalized for more efficient learning of the solution. Okay, so then here I'm defining my inputs. Okay, so these are all the inputs. They're split into training and testing. So I'm initializing the arrays, and I'm going to use grayscale type data. So that means is that my images are just 28 by 28. I don't have different channels, which you can think of the channels in this case corresponding to different vector components. So basically in my example, I'm using this type, this one, and I'm not considering the vector components. I am doing it based on the magnitude. So it's essentially you can think of it as a grayscale image when you're thinking of magnitude. Okay, so I'm learning to map the magnitude of the velocity. Okay, so I haven't tested the code for this color type, so vector field, but you probably need to modify the code for that. Okay, then I define my labels. So my labels are for all of my data, training and test, and the size is, endpoint is by endpoint. So 28 by 28 is the size of my array that I'm mapping. And here I define my mesh, so essentially the region for my data that I'm going to extract from this data set here using a mesh grid. Then I loop over all of my files. I read all my files, my input low fidelity data, my output high fidelity data. I read them using VTK XML unstructured grid reader. I will, in another series, talk about VTK in detail and provide introduction to that as well. But for now, I'm just using a VTK reader to read my data. I'm setting up the points for interpolation, and I'm probing my data based on this structured grid that I created here and saving that. Okay, so at the end of the day, I have this for every eye, so every image, which is 400 of them. I have my inputs, which are basically the low fidelity. So this low fidelity data. Those are my inputs, and my outputs that I want to learn in this case are the high fidelity data. Okay. Then what I do here is that I take the data, I split it using this train test split function here. I split it to randomly, and you can set the random order here. I split it to train and test data sets. Okay. Then what I do is that I create the data in appropriate formats. I set it to a certain format. I need to rescale the data to get it to appropriate format for PyTorch. If you're using CUDA, you need to also add this part. But in this specific example, you run it on an M1 chip on Mac, and it was decently fast. I didn't really need to use CUDA. And then I set the batch size. So the batch size in this case is it's basically if you use a smaller batch size, that's like how much of the data every time you're using to calculate your gradient for the stochastic gradient descent. If you use a smaller batch size, you will add more noise. So you'll use more of the stochastic gradient descent features, but the problem is that the code will take longer to run. If you make a batch size very large, you'll essentially get closer and closer to a more deterministic gradient descent optimization. Okay, and this is number of epochs, is how many iterations you have. So for batch size, by the way, typically we, for a small data set, 64. If you have a large data set, maybe 256, 512 are common values. But if you have a very, very large data set, you need to set this to a much larger value so your code runs more efficiently. Okay, so here I get my data into a train loader, to a test loader. So this is my training data set, my test data, or really the validation rather. And then I define my criterion, which is mean squared error loss. You can use different types of loss here too. And then also I select the model I want out of those neural networks that I talked about in the top. And I initialize that. And I loop over all the epochs. I essentially iterate basically. And I get the models. I initialize the gradient. I give the images that are selected from the data loader. I get an output based on my model, calculate the loss based on the criterion, do backpropagation using loss.backward, and update the optimizer. And the optimizer is defined up here. You select the learning rate. I'm using atom optimization. You select the model here, and you set the learning rate here. And then I am printing the loss every 5 epochs in this case. And every 400 epochs, I'm saving the model to the PT file. I'm overwriting the model. And every 20 epochs, I'm putting the model in evaluation mode so I can just test the accuracy of the model using the validation data set that's not used in the training. So here I'm just passing the validation data to the model and printing the validation loss. Okay, so that's how we do this training. So in the next tutorials, I will talk about how we can do physics-informed neural networks with PyTorch.